All right, so this is the last video of the memory mapping series. Okay, so in this video, first of all, we're gonna walk through a few representative page replacement workload examples. Okay, um, so basically the workload examples, we're essentially looking at a simple workload. And this particular workload consists of a working set that that spans 100 pages, 100 unique different pages, okay? And the workload issues 10,000 memory access requests on top of these 100 unique pages. And this is a workload. So we can kind of think of this workload as some sort of, repeated accesses, repeated requests hitting on a smaller set of data, okay? And here we're looking at 4 individual replacement policies. And the very first one, belated is optimal, OPT, and LRU, FIFO, and random, okay? So here, this slide, it shows the performance for a workload which is called non-locality, okay? So within this so-called non-locality workload, by non-locality, I mean if each reference within the workload is to a purely random page within the set of the accessed pages, okay? So let's say the total set of access pages is 100 unique pages, and each and every reference, so each and every one of the 10,000 access references is to a random page, randomly drawn from those 100 unique pages, okay? So this is non-locality. And here, this two-dimensional plot shown in this slide. So how to interpret this is, if you take a look at the x dimension, it shows the cache size in terms of total number of blocks or total number of pages, okay? Blocks is essentially equal to pages. So this is the x dimension. And the y dimension is performance in terms of read-hit ratio, okay? Read-hit ratio. Of course, the higher the better. If we're talking about performance in terms of Misc ratio, obviously the lower the better, right? So here, the very first strong pattern that we locate, we can spot from this figure is this yellow colored curve, which is corresponding with belated OPT, right? And all the red 3 online algorithms, LRU, FIFO, and random, they are essentially overlapping with each other, okay? So why the OPT is better than the rest of the 3 online algorithm is because Belated's optimal algorithm, it assumes that the algorithm has perfect future knowledge. It knows about the future so that it could make the most optimal, the best performance decision, okay? So if you take a cut over here, right? Let's say the cache size is 40 pages, and the distance from the y dimension is the performance difference, okay? So as you increase the cache size, eventually this difference gets smaller and smaller, okay? Eventually they converge to a single point at the largest cache capacity, at the largest cache size, which is 100 pages, okay? So that means this cache is large enough to be able to cache all the different pages within this working set, within this data set, okay? Obviously, for the largest cache size, you could achieve the highest cache capacity, the highest cache hit rate, which is 100%. So that is where all these four different, no matter whether online or offline, cache replacement policies converge. Okay. So this is non-locality workload. So the second workload is called 80-20, right? So how to understand this is, if you take a look at the bottom of the slide, 80% of all the references are absorbed by or made to this 20% of the most popular pages, or what is called hot pages, right? So it infers some sort of a dead locality, because there are repeated memory accesses that are targeting those popular pages, which occupy kind of 20% of all the 100 unique pages. Okay, so again, this plot, two-dimensional plot, shows the performance difference as a function of the cache size. The y dimension shows the performance in terms of hit ratio, and the x dimension shows the cache capacity in terms of total number of pages that could be cached. Okay, so again, let's use the same rule. If you fix a certain value in terms of the cache size, let's say let's pick 30. Okay, and we do a cut, and the corresponding y, if you take a look at the value from perspective of the y dimension, so these are essentially the performance achieved by a different cache replacement policies. And at the top, the most optimal, the best cache replacement policy is obviously OPT, right? Which is somewhere between 85 to 90. Let's say this is 87. Okay, and then the next one we're looking at, the second level, is LRU. So LRU is above 70. So let's say this is 70, so this should be 75, somewhere around that. Okay, and FIFO and random, as you can see, both FIFO and random, they achieve almost identical performance in terms of hit ratio. So let's assume this is 65. Okay, both FIFO and random. Okay, so as you can see, for this 80-20 workload, which exhibits some sort of data locality, temporal locality, right? So this is temporal locality, right? So by definition, temporal locality means the later reference basically largely repeat what has been seen previously. So this is temporal locality. And this 80-20 workload kind of exhibit this data locality, temporal locality. So that is why LRU performs the best for all of these three online cache replacement policies, because it uses a very simple and straightforward heuristic and try to mimic the behavior of the latest offline. But the only difference is that LRU is not make the decision not based on the future, but basically based on the historical data, based on the history. Okay, so it turns out to be suboptimal and significantly better compared to FIFO and random, which do not preserve this kind of intelligence. And FIFO achieve exactly the same as random, and this is because FIFO is kind of like random in terms of this 80-20 repetitive workload. Okay, so this is the second workload. And the third workload is called looping sequential. Okay, so this is essentially sequential scanning. So by looping sequential, if you take a look at its definition at the bottom of this slide, so it means this workload kind of looped the very first 50 pages starting from 0 all the way to page 49, for a total number of 10,000 accesses. Okay, so this is a sequential workload. So let's see how it performs. So let's first take a look at the OPT. Okay, so OPT achieves again the highest, especially for the very first 49, the very first 49 data points. Okay. So if the cache capacity is smaller than 50 and is 45, as you can see, both LRU and FIFO, they basically achieve a zero performance. Why is that? It's because LRU tries to predict the future, but use the historical data to predict the future. But within this looping sequential workload, there's no pattern at all to capture. It's just simply scanning through, the very first 50 items from 0 to 49, and then looping back, like a back and forth, right? Back and forth. Okay, so how LRU works is it tries to cache the very first however many data. But given that if we're talking about a cache capacity of 49 instead of 50, so before it reaches since it already reaches the capacity, which is 49, it has to evict the oldest item, right? Which kind of preserve the behavior of FIFO. And then it turns out the next reference is the data that you already evicted in the previous operation. So this whole pattern repeats. So that is why we end up having zero performance for LRU. And the same thing for FIFO. And especially in the context of this looping sequential, LRU kind of resembles the behavior of a FIFO because there's no pattern at all. It's not like, strictly speaking, there's no pattern. We do have a pattern. This pattern is just sequential scanning, sequential access, okay? And LRU is kind of bad for this kind of workload. And as you jump from this data point somewhere over here to the next data point, and you have a significant jump in terms of performance. And the performance instantly shift from 0 all the way to 100%. And this is because as long as you have a large enough cache, which turns out to be from 50 all the way to 100, so that you're able to cache this whole working set, which only consists of 50 pages. Remember, the workload characteristic is it always loop through the very first 50 pages, so that you're able to fully cache this whole working set size of this workload. So that is why we end up with the best performance, okay, for all of these 4 cache replacement policies. And another important takeaway, another important observation is if you take a look at the curve, the random curve, this curve, right? So it's significantly better, and it increases actually as you enlarge the cache size, right? From 0 all the way to 48, right? This is because random doesn't try to predict any particular interesting pattern at all. It just randomly, evict data and randomly make any decision. And turns out this dumber policy works best for all of these 3 online cache replacement policies. And obviously, the best ever is the latest OPT, right? So we just direct connect from 0 all the way to the best. So this is OPD. Okay, so this is some interesting workload to know about. Okay, so moving on to the next topic, threshing. So what is threshing in the context of a cache, especially operating systems memory cache or page cache? So according to its definition, threshing is also called high paging activity, where the operating system is spending more time doing this I/O, doing this paging-based I/O operations than executing programs, than making meaningful progress for the user level applications. So this is called, so this high paging or high I/O related, high paging related I/O operations, this is called threshing. So the question is, how can threshing happen? So what is the cause of the threshing activity? Because this is something bad, right? This is something undesirable. So the most straightforward example of the reason for threshing is, so let's assume the operating system has a certain objective, and this objective is to improve its average resource utilization, for example, CPU utilization. So at the very beginning, so assume we're talking about multi-program operating system or multi-process operating system where there could be multiple processes that are concurrently running, concurrently sharing the same set of CPU cores, right? So at the very beginning, there's only one or two programs that are concurrently running. But the overall objective of operating system is to improve the CPU utilization. So it keeps admitting in more and more programs with the hope that they could effectively increase this average CPU utilization. But because the different programs, they consume memory, right? Some are more memory intensive, some are less memory intensive, but they do consume memories. So as the total number of programs that you admitted into the memory become too big, then these different processes, they compete the pressures, the limited memory resource. Okay, so that operating system observe the memory cache is running out of space. So it has to make the decision with regards to which one to keep in memory and which one to evict out of memory, so as to make new space for some other process to be brought into the memory so that they could run, right? So this whole process happens back and forth, and this introduces a lot of I/O operations. And eventually, the total amount of time spending just on doing paging or the disk I/Os outweighed and exist the time for making meaningful progress in terms of program execution, and that causes the activity of threshing. Okay. So this slide, it shows the CPU utilization as a function of the degree of multi-programming. It's a two-dimensional plot. So the x dimension, it shows the degree of multi-programming. So as the degree of multi-programming increases from 0 all the way to somewhere over here, we could observe gradually increased CPU utilization if you take a look at this y dimension, right? But all of a sudden, there's a knee over here. So there's a knee at the second half of this curve. And this angle is where threshing starts to occur. So this angle, this knee point, is actually corresponding with a certain degree of multi-programming. So empirically, as long as you the total degree of multi-programming, the total number of programs that you admit into the memory exceeds this certain threshold, right? And the system starts to thresh. And the ultimate result if you take a look at the Y dimension, is the dramatically reduced CPU utilization because of the operating system spending more time doing paging rather than executing programs. Okay, so this plot basically illustrates the direct effect of thrashing into resource utilization to the overall performance. So the question is, how should we avoid such kind of bad behavior from happening? Well, so to proactively avoid thrashing, earlier batches of operating system, earlier generations of operating system, they did admission control to only allow to run a subset of processes. So they do this proactive admission control. So it always guaranteed that a limited number of programs could run concurrently. Okay, so this is some proactive admission control. And some later generation of operating system, they takes more so-called draconian approach, right? For example, some Linux distros, they run an OM out-of-memory killer, a daemon in the background to choose a memory-intensive process to kill it, right? Whenever you detect this process is too memory-consuming, and for example, this process has a severe memory leaking kind of behavior, it triggers this OM killer daemon, and OM killer daemon just kicks in and terminates the execution of this particular program, which is currently leaking memory. Okay, so these are two different approaches, proactive versus reactive, about how to prevent thrashing from happening. So there are some root cause or theoretical cause of the thrashing. But before jumping to that, let's first do a review of what is called demand paging. So recall in our previous lecture, we've talked about demand paging. So the activity of demand paging is the activity to bring a certain page from the external secondary storage into the memory, only when it is demanded, only when it's needed. And it has a certain objectives. So the major objective is to optimize performance, because the less I/O you have, the better performance it turns out to be, right? So besides demand paging, we've also talked about swapping. So what is swapping? So swapping is you preserve a certain portion from the secondary storage, a certain portion of the partition, solely used as the swapping space. So whenever you are running out of, operating system is running out of memory, you evict those pages from memory to the disk, and use this operation is called swap out. And at the same time, for the data of request that you want to bring in from secondary storage into the memory is called swapping in. Okay. So this is the difference between demand paging versus swapping. Okay, so how does this demand paging correlates to the activities of thrashing, right? So first of all, let's examine, why does demand paging work? Because of this locality model, right? Demand paging essentially exploits and leverages this date locality or spatial locality, right? So let's say if you want to bring in a program, and this program consists of multiple libraries, lib A, lib C, lib B, and lib D, whatever, right? It turns out lib C is one of the hottest. Out of these four, you just first bring in lib C because it tends to be accessed like frequently. So the rest three, lib A, lib B, and lib D, they are relatively less frequently accessed. So they are cold. So rather than bring them into the memory and wasting the memory space, why not just leave them out in external secondary storage? Only when it's being needed, then bring it back into the memory. So this is because we leverage this date locality, right? And we use memory as a cache. And the second point, why does thrashing occur? So in theory, thrashing has something to do with the aggregated size of the locality data, right? So let's say, so this is a memory capacity. Physical memory. And this is, let's say, 2 megabytes. So the operating system want to bring in more processes to basically increase the level of multi-programming or to increase the total CPU utilization. So it brings in first, process A. And PA has its own unique locality size, which turns out to be, let's say, 0.5 megabytes. And at a later point of time, the operating system brings in a different process B, right? And process B turns out to have its own size of locality, which is worth of 1.5 megabytes. The operating system still keeps in bringing in new program, which is program C, PC. And right now, since the memory has already been occupied by both PA and PB, because the locality size of PA and PB aggregated size is already almost the same as the total capacity of this memory. So the operating system, in order for operating system to bring in PC, which is worth of another 1 megabyte, it has to make the efficient decision, right? Maybe just swap out part of PA's memory and part of PB's memory in order to make new room for PC. So this is the root cause of why the thrashing occurs. Because the aggregated, so this symbol means aggregated, to sum them all up together. Aggregated sum size of the locality is larger than the total memory size, the total memory capacity. This is the triggering factor of thrashing, right? Or, in other words, the aggregated size of the working set size of all the actively running processes currently admitted into the memory is larger than the total memory size. Again, either one of these two is the triggering factor of the thrashing activity, thrashing phenomenon, okay? So we've already talked about the definition of working set size. It's the number of the unique items that are accessed within a certain period of time, okay? All right, so moving on to the very last topic, okay? Impact of program structures on the memory performance. So over here, let's take a look at this example. Consider we have an array named data, and this array is a two-dimensional array, right? So the first dimension, it has 128 number of rows. Within this dimension, it further has 128 columns. So we end up having 128 times 128, this total number of elements. And let's say each row is stored within one page. Okay, if you want to draw the layout in terms of memory layout, how this a data array looks like, it looks something like this. Okay, so this is the row 0, row 1, row 2. Okay, and assume each row is stored occupied within one single page. So it turns out this is page 0, page 1, page 2, all the way to the last page, to the last row as well, row 127, page 127. Okay, so within each row, it has a total number of 128 elements. It has its column as well, right? So we have these all small elements. In total, we have 128. Okay, so this is how it looks like in terms of memory layout. Okay, keep that in mind. All right, so let's take a look at the very first example implementation, which is called program number 1. So So how to basically scan through this two-dimensional array? In this case, we first, the outermost, we use the index of j. And the inner for loop, we use the index of I. And then if we take a look at the body of this the two-level for loop, it uses I as the outer index, the index of the row, and use j as the index of the column. So if you take a look at the memory layout, so this is how exactly it works. So these are adjacent rows or adjacent pages, row 0, row 1, row 2. Okay, so within each row, it has different columns. Okay, so this is essentially I, and this is essentially J. Okay, and we have J0, 1, 2, 127. Okay, so you basically just jump through the rows. So let's first fix J over here. It's J0, right? And then the second item that you access is you change I from this to this guy. And then basically jump another stride and to the next level, to the next page, to this guy. Okay, so we end up having a total number of, if you are talking about so let's assume all the data are initially stored within secondary storage. And let's assume we are using on-demand paging to access whatever data in memory. So if the data is currently not present in memory, you fetch it from the disk, because that is the source of the data where the data is stored originally. Okay, so we end up having a total number of 16,384, this many page faults. It's only because you do this access within fixed shred, and the size of the shred is the same as the size of the page. Okay, so this is the very first example. And the second example, which is obviously better optimized. So instead of doing this stride-like access pattern, we do this scanning, sequential scanning. So where we first fix the outermost index, which is the index of the row, and we just look within each row from the left to the right. So the J is the index of the column. In this, as a result, in this example, it ends up only incurring a total number of 128, these many page faults, assuming all of these 128 pages, they are originally residing on secondary storage. So it only requires 128 paging in operations to bring in these 128 unique pages from the disk into the memory. Okay, so it benefits from, so the program definitely benefits from this so-called spatial locality, right? Because, so this is one page. To get at the very first element, you have to bring in the whole page from disk all the way to memory. And all the rest scanning, it benefits. So this is called spatial locality. Okay.